So today what we're talking about is data processing, specifically using the XDS software package. But before I dive into XDS, I wanted to kind of give us some common vocabulary to work with. So first thing off I have on the screen here is over on the left there is a picture of a rock crystal of salt, so the common sodium chloride. And this is just to kind of give us the framework. When we talk about a crystal, what are we talking about? Okay. And so a crystal is an object that is made up of smaller objects packed together in a regular repeating pattern. So in the case of sodium chloride, you have sodium ions and chlorine ions that pack together into a compact shape. And that packing is repeated throughout the entirety of the crystal. And so down in the right, we can get a representation of the sodium chloride crystal. So the chloride in green and the sodium ions in purple. And you can see this is just a small section of the crystal, but no matter where you move inside the crystal, the atoms continue to have this sort of arrangement. So it's a repeating pattern of a spatial arrangement. Okay. One of the things we talk about with a crystal is the crystal lattice. And so you can think of this as imaginary points that are spaced out at a regular repeating pattern, sort of like a grid, okay, shown here in 2 dimensions, right? And within that lattice, if you pick specific points to define what's called the unit cell, everything within the unit cell that contains the basic building blocks of what you need to construct the crystal, okay? So for example, in the case of sodium chloride crystal, that would contain the minimum number of sodium and chlorine atoms needed to then construct the full range of the crystal packing. And so if selection of a unit cell, which are various selections are shown in this orangish color on the blue grid, you can create the entirety of the crystal by translation symmetry. So you can see this parallelogram up in the upper left. If we translate it over to the right by the length of one of these vectors between spots, it would overlap. And the contents in this parallelogram would be equivalent to the contents that would be in this imaginary parallelogram that's not drawn to the right of it. And that translates throughout the entire crystal. So the correct choice for a unit cell is based on consideration of the symmetry of the crystal. And that may include rotation, mirror planes, or inversion centers when we're talking about crystals in general. It gets a little bit more limited when we specifically talk about protein or biological crystals. But then also you can match any of those rotation, mirrors, or inversions up with a translation, and they create a second type of symmetry. So the most common one we see is matching up a rotation with a translation, and we call that a screw axis. So the way a screw axis works is you take the contents of your unit cell, rotate it by a certain amount, and then translate it by a certain amount in a specific direction. And that will overlap the contents, original contents overlap with the new area that it's reached. Okay. In 3 dimensions, we refer to the unit cell constants by the terms A, B, C, alpha, beta, and gamma, and those are drawn out in the lower left. So A, B, and C are just the, you can think of the edge of the unit cell along a specific direction, okay? And the lengths of these edges are the length of that vector in that direction. So A is a vector that points along a certain axis, and it has a given length in angstroms where we're talking about molecular structures, right? And then we have the angles alpha, beta, and gamma, which are the angles between those unit cell axes. And we're not going to go too in depth about symmetry and unit cells and all that, but these are some of the terms we use, and so I wanted you familiarized with that. Kind of what are we talking about when we speak of those? Okay. And there's an important thing to note here is that these angles do not have to be and often are not 90 degrees. So in common everyday, when we think about grids, we usually think about an XYZ plane or XYZ grid with orthogonal axes. So all the angles between the axes are 90 degrees. That's great because it simplifies math when you deal with moving things around. But in the world of crystallography, we don't always deal with 90-degree angles. And then the other common shorthand that we use is we refer to positions within a unit cell as fractional coordinates along those axes of A, B, and C. And they're usually given the indices X, Y, and Z. And so you'll see something like an XYZ of 0.5, 0.5, 0.5. And that would define the center of the unit cell. Okay. And so to actually get a position that, you know, how far away from the origin is that, you would then have to calculate, we've moved half the length of A, we've then moved in the direction of B, half the length of B, and then in the direction of C, half the length of C. And then you could do the vector addition to figure out where, exactly how far that is from the origin of the unit cell. Okay. And then one more lattice term that we use is we refer to the reciprocal lattice. And this is a theoretical geometric construct, and it's useful for understanding the diffraction condition of a crystal and for kind of visualizing in our mind what's going on with diffraction. And we won't go very deep into that, but I want you to be aware of it. And then I just have some points about the reciprocal lattice and how the main one here is that the unit cell of a reciprocal lattice is defined by the unit cell of the crystal or real lattice that it's associated with. And so there are specific mathematical formulas that link the unit cell lengths of the crystal lattice to the unit cell lengths of its reciprocal lattice. Right. And then these other points are just the degree, the units of the reciprocal lattice are inverted from what you see in the real lattice. This is why when you look at a diffraction pattern and we talk about resolution, the farther out away from the center of detector, the higher the resolution is, but that higher value is actually a smaller number, right? So we go close into the beam stop, we're at 50 angstrom resolution. As we go further out, we'll go up to 3 angstrom, 2 angstrom, 1 angstrom, and so far as we go further out from the center of the detector. And it's because we're dealing with reciprocal lattice in that case. So a diffraction spot can be thought of as a vector projected from the center of the crystal out to the face of the detector. And that vector passes through a specific reciprocal lattice point, which is defined by the values H, K, and L. And the one consequence of this that I want you to keep in mind is that H, K, and L are expressed as integers. Okay. The next bit of theory that I'm going to touch on today are just 2 equations that we're going to play around with as we're dealing with diffraction data. And the first one is the structure factor equation, and I've represented it here in 2 forms. On the left, this form is the structure factor has a summation of the scattering of the atoms within a unit cell. Okay, so Fj represents the scattering factor of individual atoms that are within the unit cell of a crystal. And then on the right, the same structure factor expressed has the electron density. And electron density is generally written as rho. And that's, so electron density over, integrated over the unit cell gives you the structure factor HK and L. Okay. And then these are related to the electron density function because the electron density can be expressed as a function of the structure factor. So in this case, the structure factor amplitude, the little vertical bars means the amplitude of the structure factor. This E to the IA or I alpha value, that's considered the phase of the structure factor. And then this second part is a geometrical construct based on the position that you're sampling the electron density and the specific HKL that you're looking at. So again, I'm not going to go too much in how do we derive these, but we're going to look at today is the structure factor equation as represented by the scattering factor. And I want to point out a couple of conclusions that we derive from this, okay? So it's an unfamiliar equation to most people, but basically what we have here is we have a specific structure factor, HKL, is defined as the summation of the scattering factors of all atoms. So J represents the atoms 1 through however many atoms you have within the unit cell. Those atoms have a position X, Y, Z. So each atom J has a position X, Y, Z within the unit cell. And its scattering factor multiplied by the E to 2 pi I, and then this HXKYLZ term is just a relative phase of that X-ray scattered from that specific atom J. And it is dependent on the position of the atoms within the unit cell. Okay. And so then you sum all those up and it gives a total diffracted X-ray wave in a specific direction. That specific direction is defined by the vector HKL. Okay, so some of your conclusions that you want to keep in mind from this equation is that each and every atom contributes to each and every scattered X-ray that we measure. Okay. The structure factor, because it's the summation of a term that has E to 2 pi I, it has an amplitude and it has a phase. And so our diffraction experiment is attempting to measure something about the structure factor amplitude. Okay. So here I'm showing a diffraction pattern that was collected from a Thaumason crystal. And the things to take away from this is that you can see that the diffraction pattern is a pattern of discrete spots. Those discrete spots have specific positions, and that those positions are relative to the crystal and its orientation. And that each spot has varying intensity. So you can see on the image that we have some spots that are darker than other spots. Okay. So the position of a spot is determined by the direction of the scattered X-ray. So remember our FHKL, it's that HKL determines the position of the spot on the detector. And so therefore we can assign each spot an index of HKL. And a lot of people kind of think of the diffraction pattern, especially if you collect the whole data set, is you're sampling the reciprocal lattice as projected out to the detector. Okay. And the intensity of each spot is proportional to the structure factor amplitude. So I've represented that here as IHKL is equal to M times the structure factor amplitude, this FHKL in vertical bars squared. So it's proportional to the square of the structure factor amplitude. And the M value is just a scaling factor, and that derives from experimental conditions, things like the intensity of the incident X-ray beam, how thick the crystal is that you're passing the X-ray beam through, how much scatter you get from air between the crystal and the detector. Those kind of factors go into that scaling factor. But the important thing to note here is that the intensity that we measure in the diffraction experiment is proportional to the square of the structure factor amplitude. So therefore, when we go to process our data, the goal is to assign each spot within the data set. So remember, the data set consists of some series of diffraction image frames that are collected over time as you rotate the crystal. And we're going to assign each spot within that data set an HCal index, which indicates its position. And then we're going to calculate the appropriate intensity for that spot. And that's related to how dark does it appear on the detector face. So this processing is usually done in 3 steps. We talk about indexing, integration, scaling. So indexing, you predict a unit cell based on strong reflections, then use that prediction of the unit cell to predict where we expect diffraction spots to occur throughout the experiment. Integration, so essentially at that point, what you can have is you have a list of assigned HCals, which will tell you where to expect diffraction spots to appear within your data set. And then in integration, we take those predicted spots and we go and sum up the intensity, in this case, as observed as counts at each pixel. And the intensity of a spot occurs over some volume. So you can see clearly in this 2-dimensional representation that these spots have some area that they take up, but that's also repeated in 3 dimensions. So that's why we take consecutive slices. And so we have to sum up that intensity in some way, and there's methods to do that. And so at the point that we're finished with integration, now each HKL has been assigned some value of I, representing the intensity of a spot, and an error value called sigma I, which represents the standard deviation of the expected uncertainty of the I that's been measured. And then the final step is called scaling. And this is where scale factors are applied, and usually they're applied in a way where frame 1 is going to have a scale factor, frame 2 has another scale factor. And the purpose of these scale factors, they're calculated in such a way that the differences between symmetrically equivalent reflections are minimized. So based on the symmetry of the crystal itself, as well as the symmetry of the diffraction experiment, some of the spots that you measure are known theoretically to have the exact same intensity. And so we can use that knowledge to then apply these scaling factors to minimize those differences. And that will help us account for variations in beam intensity, variation in intensity that are due to variations in the thickness of the crystal, for instance, or even to some extent, variations due to radiation decay. Okay, so now we're going to start moving into the more practical demonstration of the XDS software. So XDS software is developed by Wolfgang Kopsch over in Germany. He's currently at Heidelberg Institute in Heidelberg. And it's not the only integration software out there. Other ones that you might be familiar with are HCal 2000, IP MOSFilm, or just MOSFilm, which is the CCP4 packages version of integration software. And then some lesser known one is Dials, which is a relatively new integration software that's being developed mainly at ALS, but with input from other places as well. And so we're going to focus on XDS because that's the main software that we use here at AnyCat for our automated pipeline that you guys know is rapid. And you saw that work when we did the data collection. And so it's good to kind of understand what's going on with the automated data processing. So XDS has a web page, and I've given it here in this presentation. And then on that web page, it has specific links to a web page called XDS_DOC, which is XDS doc, which has documentation of the software, fairly thorough. and then XDS Wiki, which is sort of a little how-to on running XDS. And those are two important websites, and I personally refer to them often when I'm working with XDS. XDS doc is, I find, most useful if I need a definition of what, if I have a keyword or a specific file name that has been generated, and I'm like, okay, what does that contain, or what is that? XDS doc has very useful definitions of exactly what all the components of the software are. XDS Wiki has some of that, but it's most useful because it's a place where they've gathered together a lot of explanation of how the software works, how to run the software, and some useful tips and tricks when you're having trouble getting your data to process. And so I encourage you to go ahead and make use of those two websites. One of the things that XDS Wiki has on it is there's presentations, both just PowerPoint type presentations, but also some video presentations that they link to of how to run XDS and XDS GUI. So the main strengths of the XDS program are that it runs with no user input once initiated. This is useful because it makes it easy to script. And so for something like the rapid pipeline where we're trying to do automated processing, it's easy to just script it, and you don't have to worry about, okay, how do I give it this information that some other program might use a GUI to present. It's models, diffraction, spots in 3 dimensions. This has benefits for when you're doing fine slicing, like what we did with our data sets, where we were taking 0.2 degree oscillations. So anytime you go with these thin oscillations, it's useful to have a 3-dimensional model of the diffraction spot. And the third thing is it incorporates parallel processing. This is a benefit to you because it can make use of the multi-core processors that most modern machines have these days, most modern computers. And it's especially important for us because that means we can run it using our computing cluster here at AnyCat and get a lot of speed in our processing ability. Okay. So the basic way that XDS works is it has a single file called xds.inp. And in that file, it's just a list of keywords and their assigned values, okay? And the way it's set up is that you'll have the keyword and it's all in caps, and that's important that you capitalize it because the program will crash out if you try and spell it with lowercases. It does not have anything that allows you to use lowercase to define a keyword. They're all uppercase values. And then an equal sign and then the actual value for that keyword. Right. And then within the xds.inp, if you put an exclamation point on a line, then everything after that exclamation point on the line is completely ignored by the program. And so this is useful for commenting things within the input file. A line may have multiple keywords on it. And again, keywords are always capitalized. So once you generate this xds.inp file, you can run XDS from the command line by simply being in the directory where that input file is and typing in the command either xds or xds_par. And in almost all cases, you're going to want to run xds_par because that takes advantage of the parallelization that I was talking about on computers. Okay. And then finally, what I'm going to show you today is XDS GUI, and that's just simply a graphical interface that wraps the XDS program. Some of the benefits of that is that it incorporates an easy way to edit the input file, and it also presents the log files and graphs in a kind of easy to access way. Right. So that's the end of my presentation. what we're going to move from here is some of the parameters that we're going to need for processing data. And so I'm going to show you how to retrieve those parameters by looking at the results in Rapid. So in this case, I'm just pulling up one of Professor Kung's data collections from last week. And if we go to runs, if you go to a run that you're going to try and process, so let's say this one here, if you right click on it, on the name, you see it has the option to view, and then it pops up header. And if I click on that, it will give me information about the image file name, when it was collected, and various parameters of the data collection. The important things you're going to want from here are oscillation range, the wavelength, the detector distance, and the beam center. Okay, and this presents the beam center in millimeters. Unfortunately, what XDS wants is the beam center in pixels. So although this is useful to get it, and then you can calculate based on the pixel size, I'll show you a different way of getting that beam center that Rapid uses. Okay, but if you for some reason did not write down the parameters of your data sets when you collected them, coming in here to Rapid and right-clicking View Header is an easy, simple way of retrieving those parameters. Okay. Now, for the beam center, what I would do is go to Detail, and unfortunately, Rapid sometimes does that. Okay. Now in Detail, I don't want the pointless log. I want to go, so I just clicked on where it says click to view, it collapses that log file. And I want to look at either integrate or correct.lp. If I click on that, and then I'm looking for ORGX and ORGY are the values that you're using. So that's origin X and origin Y. So that's essentially the X and Y coordinates of the direct beam of the experiment. Okay. So one other thing that Rapid does is in the data that you downloaded. So here I'm again looking in that same data collection trip. I'm just looking at the files that were created from that trip. And I've gone into the main directory, so you can see Kung_E_6322. And if I do an ls here, it's got two directories, images and process. So now if I switch over to the process directory, it's got another directory called Rapid. And if I go into that, and now go to integrate, now it has a directory for every data set that was collected for that data collection trip. Okay. And inside those, is going to be this bzip tar file. All right. What that contains, if I expand it out, so you can expand that by typing tar -xjf, and this has to be Linux or Unix to do this. And then the name of the tar file. Oh, it's because I'm not, don't have permission, but you can see what that contains. What it would do is it would expand out these files. And these are files that are generated by Rapid during processing. Okay. And the main one that you might be interested in is this xds.inp file. And that is the input file that Rapid uses. And so you can actually just pull that out and use that as an input file for your own processing just making sure to make some adjustments that I'll show you in a second. Okay, so let's go ahead and jump into processing with XDS. And so what I have here is I've just created a directory that I'm going to do the processing in. And real quick, I'm going to show you how you might run it from a command line. So in this case, I'm going to copy so this GTDA underscore AH3R blah, 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 XDS.imp. That's a input file generated by Rapid that it used to process a data set that we're going to look at, okay? And now I'm copying it over into my processing directory that I've called XDS Live and I'm going to rename it XDS.imp. So XDS wants to see all right, so XDS wants to see the file name XDS.imp. If it's named anything else, it's not going to recognize it as an input file. So you want to make sure that that gets changed, okay? And then I'm going to show you using VI, the XDS.imp file. You can use any command line editor. If you have a, if you prefer GUIs, I think the most common one is gedit, which will do a graphical editor. It's fairly simple. I think this is an example of gedit. So I had it open for a different one. So you can just see I can, in here, use my arrow keys to move around or just click on a position. Or you can't click, you can move it around, but then I can get in there and edit it. So VI is a little bit more complicated, but it's something I'm familiar with. And it's useful to learn how to use one of these command line editors, because sometimes you don't always have the ability to access the X forwarding that allows you to use graphical interfaces. So if you can learn how to use VI, even the basics of it, or something like Emacs, EMACS, it can be very useful as you continue your career in science. So this is a rapid XDS input file. It's got a lot of information in it, but some of the key things, so up at the top are just data set dependent parameters. So it's going to have the beam center in pixels, detector distance, oscillation range, and the X-ray wavelength, okay? It then has the name template of data frames. This is telling XDS where to look for your data. So when you first pull this out of the Rapid by expanding that tar minus XGF, it's going to have a data file path that's consistent with our data storage. And it's not going to be consistent with your data storage when you downloaded the data. So you definitely want to come in and check this name template of data frames and make sure that that's accurately pointing to where your data frames are. So in this case, I'm backing up a directory, then going into data, and then the name of the data set, and then the file name. And here, the file name is given with this wildcards of a question mark to represent the number portion of the frame number for the data frames. Okay. So then once you change the name template of the data frames, you would want to go all the way to the bottom. And in this case, you want to look at these things starting with maximum number of processors. So when you get this from Rapid, it's going to have maximum number of processors equals 8, 4, and then maximum number of jobs equals 8, okay? And if you tried to run it with that that number of processors and number of jobs on your laptop, for instance, or even on your desktop is going to stop functioning as long as it's trying to process the data, because it's going to use up a lot of the resources. So you want to make sure that you reduce that down to something more reasonable for the situation that you have. And I'll show you that when we get to XDS GUI. The next thing you want to look at is job equals. Okay, this is where it actually tells XDS which steps I'm trying to do. And in general, what you want to do is start with all of these uncommented, and that would run through the entire process of XDS. And again, I'll show you that again when we get to the GUI. Include resolution range just tells it what resolution you're looking at, so a low resolution limit and a high resolution limit. If you're trying to reprocessing something from Rapid, you might want to give a smaller value for the high resolution limit. And then the data range is the number of images in the data set. So I would go ahead in here, make the changes to the input file that I needed to do, and then I would come back to the command line and type the command XDS_par, hit execute, and that would run XDS. Okay. Kind of give you a better idea of what we're doing, I'm going to run XDS GUI and show you how to run from there. Before I do that, so you can run XDS GUI if you have an input file already in the directory. It will read that. For this case, I'm going to actually remove that so we can see how to run it from the get-go. So XDS GUI, and this is a case if you're using VPN to connect to, and then SSH to connect to the lab computer, for instance, you'd want to make sure that you enable that X11 forwarding that I talked about in the two little articles in Classroom on how to connect to the group desktop from either a Windows or a Mac machine. Okay, so this is XDS GUI. You can create a new folder or choose a folder that has a project in, but generally what I just do is I run it in the folder that I want to use for that project, and it will use that. You go up to the top, you go to Frame, and then click on Load. Here we're going to select where our data is. So in this case, I know it's just up a level in data, and then within data, in that GTDA, and I will click on that. And you just have to click on any one of those images and say open, and it will open up an image. So the first thing you want to notice is that this is not the best image for viewing your diffraction pattern. Okay, you can come over here on the right and you can adjust the brightness and you can adjust the contrast, but you're still not going to see very much on here. Okay, and there's a couple of reasons for this. One is it's just not that great of a display for diffraction images, but the real reason is that we're using fine slicing for our images. So this is only a 0.2 degree angle sweep, and therefore the spots are very small and relatively weak compared to what you see when we were doing snapshots, for instance, during data collection last week, where you were doing 1 degree oscillations with 1 second exposure. These are 0.2 second exposures, 0.2 degree oscillation. So it's going to be very hard for you to see the spots, especially as it's coming through Zoom. I can barely make out a few of them on here. So XDS GUI is not what you use to look at your diffraction data. Use remote or use something like ADXV to look at images offline. but we have this loaded in. Now I'm going to say generate XDS.imp. And what you can see is it's coming here, it's drawn a circle around the detector, right? And that circle is big enough so that it comes about halfway out from the corners. So sort of the limits that people think about when they're doing detector limits are the edge of the detector, which can be defined as a radius from the center. Okay. Then this is what they call half corner resolution. So if you can imagine stopping at the edge of the detector, it's going to draw a radius somewhere in that area here. So we want to include a little bit more data. So we're going out about from where that radius of 1 would be out to another half. And then there's also something called full corner resolution, which would then draw that circle out so that includes the corner of the detector as well. The green circle and then the crosshair in between is representing where it thinks the beam center should be. In this case, because we just generated the XDS.imp, it picks the center of the detector. The red lines are masking out areas between the various chips that are in the detector. So the detector is a mosaic of active chips that can detect X-rays. And so on the image, you get those white spaces, which are the spaces in between the detectors. It's there is a physical gap between those chips, but it's not as large as what you see visually when they present it. They just separate them out so that it's clear that they're individual individual tiles. And so then for the actual processing of the data, we just mask those off, and that those red spots are showing that it's been masked off. You can also draw any regions you want to mask off with the untrusted region, either as a rectangle, an ellipse, or a quadrilateral. So the way to do this as a rectangle is you just pick a spot, think of it as one corner of the rectangle, and then the second corner. So that first click, and then drag it out to the size that you want. I'm just going to put it inside of one of these gaps, and then the second click should define that. Oh, it's a right click. So in that case, the 2 clicks are right clicks on the mouse. Okay. An ellipse is similar. You can either do it as a, think of this as you're defining the rectangle in which the ellipse is inscribed. So if I right click once, as I drag out, I can make it more circular. I can make it really elliptical. I can make it bigger or smaller. And then it's going to mask out that region. And then when I got that set up the way I want, I can right click. So those are useful if you have large beam stop shadows. Sometimes you'll see those depending on which beamline you collect data at. Those are more or less obvious. Okay. Anyways, we hit generate XDS.imp, so we have that now. And in here, it kind of highlights the important things that you want to check in green. So the beam center given in pixels, org X, org Y, the detector distance, and then between that is the oscillation range and the starting angle and the X-ray wavelength. Okay. Here, I don't have to worry about the name template of data frames because I generated the XDS after loading in an image, so it knew where to find that image. So that's correct. And then the defaults for XDS GUI is it's going to take the whole data range, 1 to 600. And then for spot picking, it uses half the data set, so it does 1 to 300. And you can look into various ways of doing that, but that's a good compromise. The bigger your spot range, the longer that the spot picking step is going to take. Space group number is where you can define, if you know your space group, You can define that here. All the space groups are given a specific number according to the international tables of symmetry used for crystallography. Unit cell constants would be the unit cell constants of your crystal. If you give it a space group number of 0, XDS assumes that it's unknown and then will try to predict what it is and give you a guess that. We'll see that later. Include resolution range is where you can set a high resolution limit if you want, in a low resolution. In our case, we generally prefer to tell it to go to something lower, a low resolution of 200. Now, in actuality, that low resolution limit is going to be masked off by the beam stop, but the low resolution that we can detect is actually lower than 50 angstroms, and so we don't want to exclude any information that we don't need to. Okay. And then if we have an idea of high resolution, we can put that in. Otherwise, it's going to go from the center of the detector out to the region defined by the trusted region that we see below. Okay. If you put 0 in, it just does the entire trusted region. Friedel's law. False is what you want to use if you're going to do anomalous data. So Friedel's law just simply says that a diffraction spot with the indices H, K, and L should be equivalent to the diffraction spot minus H, minus K, minus L. Okay. And this condition is true if you don't have an anomalous scatterer. And generally, you know if you have an anomalous scatterer because you've done something to your crystal setup, either your protein prep or your crystal setup, to include something that's going to diffract anonymously. So we can change this to true because we know we're just doing what's called native data. And then trusted region is that region defined by the blue spot, okay? And so 0 is the center of the detector, and then 1.2, this is referring to how far out in the radius. So 1.0 would be to the edge of the detector. 1.2 is out partially into the corners. And then if you wanted to use the entire, all the way out in the corners, you would use, the second number would be 1.4143, which is of course the square root of 2. All right. After that, these other values are just read in. The default is usually sufficient. Okay. NX, NY is the number of pixels in the X and Y direction. QX, QY is the size of the pixels in the X and Y direction. And that is included here, as it says, to make the correct step happy. It can actually derive this from the frames natively if you have that. All right. And then the other thing at the bottom is the untrusted rectangles. These are all those red rectangles drawn in here, just defined. And they're defined as the upper left, the far left column, the far right column, the top row in pixels, and the bottom row in pixel numbers. So you can think of this in the X direction and the Y direction. So these rectangles up here are these long ones here that go from 0, which is the left side of the detector, to 4150, which is the right side, and then some span of the Y direction. And then we have three vertical here. That's these vertical ones. And then these extra ones are the rectangle and the ellipse that I drew in on the detector face. Okay. Okay. So the only other thing you would want to add in here is maximum number of jobs equals, I use 2, and maximum number of processors. We're going to set that to 6. Okay. How do you decide on this? Okay, so this is my system monitor, and you can see that it thinks it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 CPUs. Okay. What it has in this computer is 2 hexacore processors. So generally what I do is I set my number of jobs equal to the number of actual physical chips that I have, and then the number of processors equal to the number of processors within each chip. So these are hexacore, so each chip has 6 processors in it, and I have 2 chips in there. And so that's an easy way of dividing up. You can actually increase this a little bit. So if I have 12 processors total, I could maybe say 4 jobs and 4 processors. Each job will try to make use of the maximum number of processors available. And so you could see that that would try to make use of 16 processors. So even though I only have 12, it can adjust. So you don't have to get this 100% perfect, but you want to be careful. The more jobs and processors you use, essentially the more memory that the processes try to access. So you're limited by the number of processors you actually have, right? But you're also limited by how much RAM you have. In my case, I have 12 gigabytes of RAM. So why do you want to increase these? Okay, so I have an example here, a data set that was collected 450 frames at a detector distance of 300 millimeters, run on our cluster, which uses jobs equals 8 and processors equals 8. For the integration step, it takes 15 seconds per job, for a total time for the integration step of 28 seconds. Okay. When I run that on my desktop, okay, I use jobs equal 2, processors equal 4. It took 110 seconds per job, for a total time of the integration step of 115 seconds. So you can see that by increasing jobs significantly, you can get much faster data. And then if I do jobs equal 4 and processors equal 4 on my desktop, I can squeeze that down to 92.9 seconds for integration. But in that case, I'm also maximizing the amount of memory that I'm using. So you got to kind of play around with those parameters to see what works for your hardware. Okay. So normally, if I was just running this, normally I would put 2 jobs, 6 processors. I'm going to lower the number of processors down to 4, and that's because I'm also running Zoom, which is using some of my memory up. So I don't want to overload the computer. Okay, and I see Edwin had a chat question. How often do you need to adjust trusted region, and is it something you need to consider for every data set? Usually this is something that people just have a default that they go to. Most of the time, when I collect a data set, I try to make sure that the entirety of the resolution spots that I can see, and therefore would anticipate collecting, are within the edge of the detector with some room to spare. And so most of the time, I would be fine with a trusted region of 0 to 1.0. Okay. Occasionally, I underestimate how far my crystal diffracts, and so I can see on my diffraction frame, bump that back up, that I might have diffraction out in this area that's visible to the naked eye. And if I can see it with the naked eye, then the computer definitely can see it. And so in that case, I might bump that trusted region out. In this case, just sticking with the default of 1.2 is perfectly fine, because if it doesn't find data out there, you're going to end up chopping the resolution back anyways to where your resolution actually exists when using the include resolution range as we run the process. So, all right. So I've gone through, I've set all the parameters. The only one I'm not sure about is the beam center. Because in this case, I'm not looking at Rapid to see what it said the beam center was. But I'm doing that on purpose so I can show you how you can check whether or not that's a good estimate or not. If you pull it up and it doesn't read it in, I think this reads it in from the frame header. And so it automatically marks it, but you may not get it marked. In that case, what you can do is you can kind of go to the center of the detector. Okay, so see my mouse is sitting on the center here. And then over in the upper right of the image, so I'm looking at this area here where it says pixel value, okay? It gives me an X and a Y value. I can use those as an estimate for the beam center if I'm not sure what that estimate is. Okay. In this case, I believe it read it from the header.
Hey, David, can you like more a header and just show them what our headers look like?
Can I more a header?
Yeah, that's how I always look at headers. I just more them. I more the file.
Yeah. All right, so this is the directory where my data set is. So I'm going to just more. This is the header. So in here, you can see that it has exposure time, it has detector distance, it has beam XY in pixels. It's got the starting angle, all those parameters. So that's one way to look at it as well. The thing to remember is that not all beamlines have their headers set up to report that information. So you want to, if you're at a, if you're collecting data from any given beamline, as you're collecting the data, you want to make sure that you know what the header, the beam center is for that beamline. Whether, you know, they might tell you, oh, it's in the header, you don't have to worry about it, that's fine. But if it's not in the header, you want to make sure that you write it down so you can have an accurate guess of that. Okay. So we made our adjustments to XDS. We're going to save it. And now the run XDS becomes active. I'm going to click run XDS. And you can see over here in the background, it's updating stuff on this screen. That's just running the normal output that you would get from XDS. And then as it completes each step from the job, it produces, it highlights these tabs so they go from grayed out to black, and you can look at the various tabs to see what's in the log file. So XY correction is just a spatial correction that takes account of some of the geometrical distortions for the detector. It's bases this off of in the XDS.IMP. There should be a background range. If it's not given, there's a default value that it looks at. Okay. And so it looks at that. One thing I did forget to mention is in the input file, it will say what it thinks the detector is. So in this case, it thinks it's a Pilatus because we're looking at .cbf files, but in actuality, this detector is an Eiger. The fact that it says it's a Pilatus actually doesn't make a difference as far as processing. I don't think anyways, but you can come in here and correct it to Eiger and reassure that that's correct. So then the init step is another initialization. It just reads in parameters and gets it set up for doing a peak picking. So it looks at the background images to kind of see what the background count is overall, and therefore it has some threshold to determine what a strong spot is. The first one you really want to look at is cold spot. And it's currently running that, so I can see this is saying it's cold spot task number 1, and it's still putting out information. So it will be updating this as it goes. Cold spot is the first step that takes a little bit of time. So again, it's looking at the images for spot range, and on all those images, it's doing 300. So if you have a computer that doesn't have a lot of processing power, rather than looking at half the data set, you might want to look at a quarter of the data set, or some the first 20 degrees of the data set, for instance. Okay. So on the cold spot tab, over on the right, we have these two graphs. The top graph is the number of strong spots picked on each frame number. And then the bottom graph is the number of strong pixels on each frame number. And what you're looking for here is some significant amount. What's significant? 40 per image. Maybe you can get away with 20 per image even. But it should be relatively high. It should be relatively consistent across the total data set. So one of the things we can see here is that the number of spots is starting to decrease. So this did not update properly because I restarted the XDS. So it should go all the way to 450. But you're just looking to see here in the graphs, do I have spots that are being picked as strong spots on all the frames that I'm looking at? So remember, I was looking 1 to 300, so that's why we're stopping at 300. If I was looking at the whole data set, it would have gone from 1 to 600. Okay. If you see any frames where that number drops down to single digits or 0, that's indicating that that frame is blank, which might be an indication that you've rolled off the crystal, or during the experiment, the beam was lost for some reason, so therefore you're not getting any spots on that crystal. What you're looking in the log file here is, you can see here we got a certain number of background, a certain number of strong pixels. And so you should have enough that you can feel confident that you're picking when you actually try to index the image and pick out a space group, that you have enough spots to work with. It's not, you don't have to spend too much here. Just check to see that these are non-zero values is what you're looking for. I'm going to go IDXref. Over on the right, it pops up an image. We need to adjust the zoom on. This is showing for all the frames, spots that it picked, were they then indexed or not when it selects the point group that it's going to use for indexing. So if it was indexed, it becomes black, and if it was not indexed, it becomes red. And so here, what you're just looking for is that the majority of the spots are black, and that there's not, if you have a large number of red spots, especially if they're clustered in weird positions, that would be an indication that something's gone wrong. If you have a number of red spots that are kind of interspersed throughout this image here, that could be an indication that you have multiple lattices. So some of you guys would have seen that when you were doing data collection. We might have brought that point up that, oh, here you can see that there are multiple lattices. This would be another way of seeing that, because you would have a lot of spots that are indexed and in black, but you would also have maybe an equal number or comparable number of red spots that are also interspersed on this image. So visually, that's something to look for the IDX rough step. Over on the log file, what we're going to do is we're going to look down on auto indexing is based on, so this line here, and it says we're basing it on 12,481 out of 12,481 spots. So that's telling us that our auto indexing is based on a high percentage of the spots that were found and fit the parameters used for indexing. So that's a good indication. I said one way to check. Okay, then the next thing you want to check is this listing here, cluster coordinate and indices with respect to the reciprocal lattice basis vectors. Over these final three columns here, you just kind of want to scan through them. What you expect to see are all integer values. So you can see here 1.00, negative 0.00, negative 1.00, so on. And pick another one, negative 4.00, negative 1.00, 1.00. Spot on integer values. Sometimes you'll see, oh, 2.05. That's fine. It's close to an integer value. It's not quite on it, but it's close, right? That would be fine. What you don't want to see is 1.63, negative 2.48, negative 2.25. If it's significantly away from that integer value, then something's gone wrong with the indexing. Okay, so that's another quick check. All right. In this section, selection of the index origin, okay, it gives us here XD, YD. This is the direct beam position, so that we put into the input file. Okay, and then it picks an origin based off of those and refines that. And so then down in this list of index origins, it's picked 0, 0, 0. In the refined X and Y position are at 250.9 and 2195.8. Okay, so we're only off by about 2 pixels. Depending on the detector, 2 pixels could be significant or it can be insignificant. In the case of a Eiger detector, the pixel sizes are 0.075 millimeters. And so being off by 2 pixels is not really significant. And so we can say, okay, we're pretty confident that we have an accurate estimate for our direct beam position. But if we weren't, we could actually take this XD value and then this YD value, go back to our input file and replace the org X and org Y with those values. And then rerun XDS. And that should give us a better, if we were significantly off or we just wanted to check. And the final thing we do in IDXref is this determination of lattice characteristic and Bravai lattice. We can just check and look at that, see if that makes sense. Here, what you have is a list of the various Bravai lattice types and then quality of fit. So MP stands for primitive monoclinic. AP stands for primitive triclinic. So any unit cell should be able to be expressed as a triclinic unit cell because there are no restrictions on the axes. The next least restrictive is the primitive monoclinic. In this case, one of the axes angles between axes is 90 degrees. The other two are not fixed. Okay, so in this case, we could see that what you're looking here is for low quality of fit value, what's the highest symmetry, and they go in order of higher symmetry that has a low quality of fit. Again, this is just a check for sanity. If you know that I'm working with a primitive monoclinic cell, I would expect to see a primitive monoclinic cell picked here. If you're not sure, if you're, first time you're looking at a crystal, this will give you information on what it thinks is the correct unit cell, Bravai lattice unit cell. So IDXref defines the unit cell that it's going to use to predict pixels. DefPix comes in and it actually does the prediction. Where should these pixels occur on the detector face and on which frames? Okay, so this basically it's created that list of HKLs and then also has parameters indicating their positions. So then we go to integrate. And it's upset because it broke something. So if we go okay, so what it's telling me is that it cannot find a temporary file that should exist. And so what I'm going to do is come in here and I'm just going to remove all temp files, all files with the extension .tmp. And then I'm going to try and run integrate. So IDX ran, DefPix ran, integrate didn't. So when I come back to XDS.imp, I'm going to go to my job control and I'm going to say, I want it to start with integrate. And I want to start with correct. And then I don't want it to do any of the other ones. So I put the exclamation point and commented it out. I change that, save it, run the process. Okay, and integrate is the most computer intensive step of the whole process. And so I just bringing up my system monitor, and what you can see is this trace is the busyness of the various CPUs, and then also the amount of memory it's using up. And so you can see here we're running with 2 jobs, 4 processors, and we're maxing out various CPUs, right, 8 at a time because we have 2 jobs, 4 processors. And so we kind of get this variation of processing use. If I had 4 jobs, 4 processors, what you'd see is these lines would be all topped out and maxed out at 100% for all the CPUs. And then you can see it's using up 7.6 gigabytes of my 11.5 gigabytes of RAM memory that I have.
So if you're crazy and you want to actually run this on your Mac, I would set to 1 processor, 1 job, and then you can start it and then you should just kind of walk away and come back later.
And when she says your Mac, she's talking about your Macintosh, your laptop.
Yeah.
If you have a desktop Mac and it's got, a 4 quad core processors in it, then feel free to go ahead and bump the jobs up and whatnot. The thing to watch out for is your memory. So what it's doing is it's breaking down, so if I scroll this in, the jobs into blocks of, so you can see 226 to 250, so image number 226 to 250. So it's looking at, what is that, about 25 images at a time. Each image is 18 megabytes in size. And so you can kind of do the math. How many of these can I open up, right, while still not swamping my RAM memory? So it's giving me the information for one of the jobs. There's also a second job that's also trying at the same time to open up 25 images at a time and process them. And so you can imagine if I go up to 4 jobs and they're all looking at 25 images at a time, now I'm really starting to hit that RAM hard. And you can easily lock up the computer because all the RAM is going to the XDS processes and you can't even move your mouse around because drawing that mouse takes some RAM and it can't access it. All right. So now we go to integrate. Okay, so over on the right, it's got images, graphs here for various parameters that it refines during the integration process. And those are defined basically this line here, refine, integrate. So it's gonna try and refine the beam position, or the position of spots, the beam position, and the orientation of the crystal. And so we could see in integrate, we're not refining the unit cell axes, so those just stay flat. But we are doing the beam, so there's some variation in there. And we are changing the beam divergence and the mosaicity. Okay. So on these, you gotta be careful because using the mouse will move things around. If I left click, I can drag it either way, up and down. If I use the scroll wheel, it will zoom in or zoom out. Okay, so a lot of times I'm trying to scroll this, the actual window, thinking I'm on the scroll bar on the right here. I use the scroll mouse, and all of a sudden, one of my scales just go really wonky. And that's why. So be careful of that. You want to actually scroll the window, make sure you're on the scroll bar. And the thing on these graphs, what you're looking for is small relative changes and no big oscillation swings, okay? So we're looking here at beam divergence. So one of the things you want to look at is what are the range of on my axis, right? So it may look like it's a big, if I zoomed in really close, it may look like big swings, but you can see we're only going from 0.014 to 0.018. So those aren't very big changes, even though they look fairly big steps. But if we come back and zoom out to about where it was, most of the data set is okay, but then something funky starts happening around 480. We start getting this wild swing in values, and that settles down again for the last 40 images or so, okay? So that's a clue that something's going on. Mosaicity is the same. It's relatively stable. Some change. So mosaicity, as you accumulate radiation damage, generally increases as well. And so you expect this to start climbing up the farther along the data set you go, but you still want to see relatively small changes within your data set, and you don't want to see wild oscillations. So again, we have a problem somewhere in this 480 to 560 range. So something's going on there. The scale factor, it looks like it has a big jump, but then if you look at the actual values on the y-axis, it's 0.736 to 0.776. So it's not a huge jump here. And that could be explained by if it's because crystals aren't a sphere, as you rotate them around, you get different thicknesses of the crystal that you go through. And depending on how different your thicknesses are in different directions, you can see quite a swing in the scale factor because of that. So if you think about a plate, if I'm looking down the flat part of the plate, is perpendicular to the beam, I'm going to have a relatively thin cross section of that crystal. And therefore, I'm going to need a larger scale factor because my reflections are going to be weak relative to if I'm looking with the large axis of that plate parallel to the beam. Now I'm shooting through that thick part of the crystal. It's going to have a lot more crystal volume that's diffracting, and therefore it's going to generate stronger spots relative to when it's perpendicular to the beam. So in this case, the scale looks okay because it's not a big jump. There's a jump here, but it's still relatively small. And then our detector coordinates of the direct beam are pretty stable. The crystal to detector distance stays stable and then starts changing as it goes towards 480. But here again, it's a small amount. It's 397 millimeters versus 399. One thing to note is that the detector distance is one of the parameters that sort of accounts for radiation damage. So as your crystal gets exposed to radiation, the values for the detector distance tends to change because of the spread of the diffraction pattern as radiation damage occurs. So it's not unusual to see some change in this detector distance, especially if you're seeing radiation damage. And then again, on the crystal rotation, it's small changes. The total range is from 0 to 0.7 degrees. And so we're not seeing any big changes. But the things that would cause me some concern are these wild swings in mosaicisity and beam divergence, even though the total distance of them is not that great, but based on the rest of the run, they're pretty big. So you can see most of these other ones are oscillating within a value of 0.016 and 0.02, but then here you get much bigger. And so that's a concern. You might ask what's going on, and because we know who collected this data and what happened is that the crystal wasn't fully centered, and so back around 480, it started moving out of the beam, and then it moved back in by 560. And so that's the sort of things you can expect to see if you don't stay on the beam. So that's basically what we look at on Integrate, is just these graphs. Are we seeing sharp spikes or oscillations? Are we seeing wild swings in the values? What we want is nice and smooth with minimal jumps. So this is overall looks pretty good. I might go back in and process without using this range of data from 480 to the end of the data set, perhaps. So then we move on to correct. So Integrate, again, what that step is doing is it's saying, okay, I know where my spots should be. I have some model for the shape of the spots, and I'm going to sum up the intensity over all the pixels that I would expect to contain information from the spots, and give myself now for each pixel, each diffraction spot, I've assigned it an HKL, I've assigned it an intensity value, and I've assigned it some estimate of the error in that intensity. And then the final step is correct, and this applies some scaling factors and does some more refinement on some of the parameters as well. And then, so again, we have graphs on the right. Some of the things to look at are your I over sigma. So this is over resolution. So this would be an indication of, okay, where is my diffraction no longer really significant, right? R factor observed also can be used as an estimate of the effective resolution of the crystal. Completeness of the data, this is over the data range. So you can see as we add more frames, we're getting closer and closer to completeness. So if we look back at Integrate, remember I was thinking, well, maybe I want to eliminate past frame 480. Is that reasonable? And here I can look and I can see at 467, I'm up and I've got a relatively high percentage of completeness, which means that if I do decide to cut the data set from 480 out to only look at the first 480 frames, I'm still getting most of the data that I would need to solve the structure. And so it would be reasonable to go ahead and do that cut to 480. And then these values are actually presented, if you scroll down, usually the best way is to scroll all the way to your bottom and then start scrolling back up. Until I find this table here. So it's going to say completeness and quality of data set, and it's going to have that. So you got to be careful. The reason I scroll all the way to the bottom is as it's going through the process, it gives similar tables, but this is actually for data range 1 to 201. Okay. 1 to 267. So as it's actually processing through, it updates these statistics. So I want to make sure I scroll down to the last one of those given. And I can check if I'm doing a search. It's preceded by the statistics of saved dataset XDS ASCII HKL. Okay. And then just scroll down from there and I get this completeness and data quality. And then if I make this over, so here what we have is the subset of resolution limit. So the way that integration works is it looks at subsets, what they call shells, resolution shells. So this is the high resolution limit of the shell, and then the next shell up would start with a low resolution of that. So this first one was our low resolution limit is 200 angstroms. So this is looking from 200 to 6.54 angstroms. The next one is 6.54 to 4.63, then 4.63 to 3.78, then 3.78 to 3.27. And what it's doing is it's actually breaking the diffraction pattern down into shells that have a roughly equivalent number of observed reflections. Okay, and so you can kind of see that here. These values are roughly equivalent. Okay. So this is number of observed, the number that are unique. So observed includes all the reflections. Unique is the subset that would say if I have two that are symmetrically equivalent in the unique count, those only count as a single reflection. Okay. And then the number of possible unique reflections. So here what we want to see is that the number of unique reflections is close to the number of possible unique reflections. We can see that that's pretty consistent throughout. As you get to the higher resolution, that's going to start dropping off, right? So our high resolution shell 2.32 to 2.18, we observe 5,400 unique, but there was a possible of 13,900. And so we're not really seeing all of the possible reflections that we could have. Now, the thing to remember here is on our frame, we're integrating out to this blue line. So all this area between the edge of the detector and this blue circle here that's in white, it thinks there might be reflections there, but obviously it's not going to find any reflections there. Okay, so you're only getting those highest resolution reflections in these little sections in the corner. And so even if I had diffraction that extends out to 2.18, I would most likely see that completeness of the data set is relatively low compared to other shells. So this is the completeness of the data set for each shell in this column here. R factor, and then R factor expected. I don't worry too much about what the actual value of the R factors are. I just check, are they close to what the expected value was? And then overall, I want to look at the R factor for the lowest resolution shell, and it should be relatively low, preferably below 10% or even lower. Here we got good 5.8%. And then I'm also looking at the overall R factor of 22%. And usually that I'm looking for something 25% or below for a good data set. I might push it a little bit if I'm really trying to squeeze out data. But I know if I'm going above 25% overall R factor, that now we're starting to, the data might not be as good as it should be. Okay. As far as resolution cutoffs for XDS, what you want to look at is the CC 1/2. This is expressed as a percentage. And what it's comparing is it's split the data into two separate data sets and then doing a cross correlation. And so the statistics tell us that if we're above 30%, and there's some debate over whether it's 30%, 50%, or maybe even a little bit lower, that we should consider that statistically significant and therefore include that data. Okay. And XDS tells you that anything above the 0.1% level, I think that actually is a mistype. It should be the 10% level because these are presented as percentages. So anything above 10% would be marked with an asterisk indicating that you should probably consider keeping that data. So they're using a 10% CC1/2 cutoff. I think the standard use is 30% for most crystallographers these days, but you can use that to kind of determine. So if we use 30%, I can see my resolution is somewhere between 2.32 and 2.48. And then anomalous correlation is if you're looking for anomalous signal, here we turn Friedel equals true, so we shouldn't expect to see anything. But if we had it out false and we were expecting to see anomalous signal, what you want to see is positive values for this anomalous correlation. And again, anything above a 10% says that there might be a significant correlation and therefore useful anomalous data. Okay. So at this point, we've run through XDS. I've kind of shown you things to look at. Do you have any questions for me as far as running the program? Okay, good. I expect when you go to actually do this on your own, you might run into some issues. Again, reach out if you have questions on what to do. At this point, now you're going to, well, what do I do with this thing? Oh, before I go on, the other things you can check in the correct log file are, you can check the automatic space group assignment. So that's up near the top. And again, you have this table of Bravai lattices and what fits best. And it's saying anything with a star, it says it's a possibility. And then it goes and it actually checks different space groups. And then it decides to pick something. So in this case, we picked a Bravai lattice that was primitive monoclinic, okay? So therefore, we only have a few space groups to check. So our space group table here, space group number 1 would be a triclinic space group, and then a 3 is the monoclinic, primitive monoclinic space group. And here, what you're looking at is the R measured value. Catherine, I'll answer your question about the resolution in a second. So here, the R measure of the triclinic is sort of your baseline. And what you're looking for is the highest symmetry space group that gives you an R measure that doesn't jump up significantly. Okay, so you can see here the monoclinic is only 2 percentage points higher. So it's still relatively confident that you can select the monoclinic space group. Okay, so it tells us it's selected that space group and that these are the unit cell parameters. And so if I'm going to reprocess this or a similar crystal where I know the space group is the same, I could actually use those values as an initial starting point back in my input file. And then the other value of importance is this asymptotic limit of the I over sigma, okay? Given as ISA, right? And the people who wrote XDS, just, you know, there's a, right here, there's a citation you can look at that kind of describes what's actually being calculated here. But basically, they tell you that if you have something above a 20, that you have a pretty good data set with no significant systematic error in it. And that systematic error may be because of something with your crystal, but it also may be because of something with the beamline. So if you have a project that you worked on and you normally consistently get ISAs over 20, and then you go to a different beamline and it's giving you a much lower ISA, you might let the beamline know that, hey, something seems to be funny. I'm not sure if it's your beamline or not, but I'm getting a worse statistic on your beamline than I normally get. But in general, the other thing that can cause this is just weak or poorly diffracting crystals. If you get down below a 10, it's not a great data set. You still might be able to get useful information from it, but what you'd want to do is make sure you collect a lot of redundancy in your data. So you would want to collect a larger data wedge as that drops down. So just be aware of that. It's a good thing to check out. Okay, so now things we want to do. One of the first things we're going to want to do is change what our resolution we're looking at, right? So we looked at that.
So that's Catherine's question, is how do you reprocess the data with the lower resolution?
So we looked at this, we said, oh, maybe we want to cut the resolution somewhere between 2.32 and 2.48. So we're going to go back to xds.imp and this include resolution range, and we're going to change that to say 2.4. Okay, so that high resolution, whatever we want to. All right, so that's where you change the resolution. You can also come in here and you can change the space group number and the unit cell constants if you want to. If XDS is picking the correct one, it's perfectly fine to just leave it as 0 and it'll pick the space group and unit cell constants.
David, after you do that, which steps do you run?
So after I do that, I change the resolution. I'm going to tell it to save. And then up here in jobs, I want to rerun integrate and correct. Those are the only ones that are affected. So in this case, I've already done that because when I first ran it, that integrate step failed. So my job control was actually correct. Just integrate and correct. But if I didn't, I would just come up here and adjust that, integrate and correct. The other ones don't need to be rerun. Okay, so save that. The other common ones to change are in the beam center, right? We checked that on the IDX ref when we looked at this table here, the selection of the index origin. Right? If I wanted to change the beam center because those values are off, then I can change that there, make that change here. And in this case, I would probably rerun the IDX ref, def picks, integrate, and correct. Yes, Edwin, if you're changing resolution limits, you want to rerun, integrate, and correct. Because what's going to happen is it will change where your resolution shells are, and therefore that might affect your statistics.
And Catherine also asked, what are the output files from XDS? Like, can you give the extensions for which ones are the log files and such, like if we were looking at them not through the GUI, but.
Yeah, so if I'm looking at not through the GUI, okay, this is what's ends up being in the directory after I run XDS. So they have some that are marked CDF. These have various corrections. And basically they're given in the format of an image file. I generally don't look at them. The most critical one is actually this IDX ref, this image on the right here. This is derived from the Trying to see which one it is. It's the frame.cbf file. Okay. This CBF file actually gives the final information from the final frame. And so what XDS GUI has just done is conveniently collected that information as it comes. And so now this is actually displaying for the entire data set the spots that are indexed versus spots that were picked but not indexed, okay? And so actually XDS GUI has a much more useful way of viewing that than this frame.cbf. The log files are these ones called LP, and so each step generates an LP file. And so you can look at those. And so for instance, if I go and look at the correct.lp, this is exactly, this information here is exactly what we're seeing over on the left of the XDS GUI window. All right. The advantage that the XDS GUI does is it then graphs out these values on the right. Then the other files it has are this xparm.xds. Right. If I just look at that. This is just a format, and it's telling XDS information about the starting image number, the starting oscillation, or the starting omega, the oscillation in omega, and some other, so this first line is just about the image frames. This line here is space group and unit cell parameters, right? This is information about the detector parameters. So this is number of pixels, the 4150, 4371, and then the size of the pixels. And then this is the beam center and detector distance, okay? One thing you can do is once I've run XDS, I can actually, it then produces this file called gxparm. It's exactly the same format, but these are now the refined values. Okay, so you can see for the unit cell, the space group and unit cell, rather than having a space group number of 1, it has a space group number of 3. And then it has the unit cell values that it came up with, right? And it also has an update on the beam position, the direct beam position. So one of the things you can do is you can actually copy gxparm.xds over the xparm.xds and then rerun, integrate, and correct. And what that does is just update some of those values that were refined, right? And in fact, in XDS GUI, there's a tool here, optimizing data quality. And it's just copy latest geometry description over the previous one. And that's, in this case, they actually use the command move, but it copies the gxparm over to xparm.xds. And then the other files that you'll see are these .htl files. So there's integrate.htl and there's XDS ASCII.htl. Integrate is the list of spots. So they're HKL values. They're just go over. So what it has is this, just a list giving the HKL indices, right? All by intensity, all by the sigma intensity, and then it gives you its position on the detector in this information here. Okay. again, it's not something that you generally are going to look at. In the XDS ASCII, this is what comes out of correct. Again, it's similar. It's giving HCal values along with an intensity and an estimate of the error of the intensity, as well as positions of that. And in this case, it actually orders them based on their indices, and it will group them such that you have 0, 0, 1, and then it's the negative value 0, 0, negative 1, and so on. So symmetry equivalent, and then bifoot pairs next, and then it moves on through there. And so generally, the XDS _ ASCII.hcal is what you're going to use in the next step of the data processing. Good, I answered that.
Yeah, you anticipated it.
And so on Wednesday, when we start looking at pointless and aimless, Kay will show you how to read those in to pointless, and then pointless gives you a format that Scala or aimless can look at.
So yes, so the XDS ASCII is the file that's the same as like the .sca file that comes out of HKL 2000, but we're actually going to do some more processing on these files and turn them into MTZs before we would take it on to Phoenix or any other. So we're going to go ahead and like add FreeR flags, and I'm also going to go over what the different columns mean. I hope there'll be time on Wednesday so that we can understand those files better.
So yes, Edwin, when you rerun integrate, it will overwrite anything that it normally generates. So if I rerun integrate, it will overwrite the integrate log file, it will overwrite the integrate.hkl and any other parameters that it would write. So if you want to compare earlier runs to making a change and correct it, changing something and then rerunning it, you would want to create a backup of those results. So in XDS GUI, it has under tools, this saving and comparing good results. And it's a little button to backup files to .save. So what it does is it makes a directory called save. It copies everything from the run that's in the directory into that save directory. And so then you can use it to go back and look and compare your integration results or your correct scale, the final results from correct as well.
And like one final thing, you noticed that when David talked about rolling off the crystal, he just talked about like truncating the data set at 480 and not taking everything after. XDS doesn't allow you to basically skip frames in the middle and process them all together. If you wanted to do that, like if you wanted to have basically, let's say the first 500 frames and the last 50 frames as a data set, you would actually have to process them as 2 separate batches. And then you would have to add them together with another program, which you can basically do it with pointless, and I'll show that next time. But if you have if you roll off your crystal or you have a problem in the middle of your data set, you can't do something like data range 1 to 300 space 350 to 400, like you would think of doing it in HKL 2000. You have to make it 2 separate processes. Right.
And the way you do that, so again, we're back on xds.imp. You just go to data range here, right? So if I decided, this data set had 600 frames. If I decided, no, after 480 wasn't any good, I can say 1 to 480. Now, if I save and rerun, it'll only do those 480. The other thing is on spot range, what you can do to save processing power is rather than looking at the entire wedge of 1 to 300 in this case, or half the data set, I could actually go, so if these are 0.2 degree oscillations, if I want to say look at, make sure I look at least 10 degrees, right? So then I want, what, 5 images? I might do 10 images. So I can actually say spot range of 1 to 10, and then I can put in a second spot range. Say, I don't know, maybe 301 to 310. And it will take those as spot ranges and look, just pick spots on those things and then use that for indexing. So similar to when we did the snapshots where we looked at 0 and 90, we can kind of do something similar here where we give it smaller ranges, but we give them more than one spot range. And that can help improve, give you as good of an indexing result as you would get from doing a whole half data set, but using significantly less computing power, because now you're only looking at 20 images instead of 300 images for that spot picking profile step, that cool spot step. But you can also see that the biggest computer processing power was the integrate step. So, you know, you might save a couple of minutes on the cold spot by doing something like this, but you know, you're gonna have to let it run for 20 minutes, half an hour on the integrate anyways, or even longer if you have a long data set. It might not be worth it. Okay.
Does anybody have any more questions? If not, I will stop this recording and we will call it a day.